Alright, let's take a look at exercise 323. This is a simulation. The purpose of this simulation is to compute pi. What we do is we pretend that we have a dartboard and we throw darts into a square randomly and see how many fall inside of a circle and how many fall outside of the circle. So this is an interesting problem. It's not a graphics problem, but if you do it as a graphics problem, it is interesting to look at. But let's do it as a text, as a character-based program. So I'm going to create a folder for this, P223, sorry, 323. And let me copy from, is it 2.3? Not getting this right. It's quite slow today. Let's go ahead and put this in there. This is some code that we've run before. So what we need to do is throw darts. And let's do this. See, I'm in VI actually right now. So this is the dart throwing simulation. See if that builds. G++. Dart throwing simulation. So what we do is we have a square with corners 1, 1 and -1, -1. We have to throw the dart inside that square. That means we need to calculate an x value for the dart and a y value for the dart. And these can be random values between 1 and -1. Let me show you how to do that. We need to call this rand function. Pass in, that's not right. Rand returns a number between 0 and max rand. So we divide by max rand, that gives us a value between 0 and 1. But 0 and 1 is not good. We want the range to go from -1 to 1. So let's multiply that whole thing by 2. That gives us a value between 0 and 2. And let's subtract 1. That gives us a value between -1 and 1. Now for that to work, we need to include the some header file. Not sure which one it is yet. Let me just think about that. And let's change this to dart y. Now let's investigate. Let's see if this is in fact doing something. Let's look at doing what we want it to do. Here's dart x. And actually, let's do dart y on the same line there. Let's see what happens. Once again, we do this one step at a time. Rand is not declared. So there is a, is it C standard lib? Not sure where it is. Let's try that one. That's not it. Where is rand defined? Is that right? I went to look at that too fast. Rand max is not declared. Oh, max rand. Oh. But actually, the rand was alright. So this should be rand max, not max rand. That's rand max. Alright, there we go. This should be rand max. Build that on it. -1 to -1. Something is wrong. So this is integer division. So that's a problem. This has to be, see, this is an integer divided by a large integer. That's going to give us 0 because rand is less than rand max. So we need to make this floating point division. So it's a number of ways to do that. We can cast this to a. Here's one way to do it. We can cast rand to a double. Let's do it that way. So the numerator is cast to a double. There we go. Now look, we're going to get exactly the same number. We had this problem before. We need to seed the random number generator if we're going to get something different, but which is what we should do probably. So let's go ahead and do that. So let's go ahead and seed the random number generator. Well, we're not using too many comments in our code actually, but there's one. So it's srand times 0. Let's see if that builds. Looks good. Should get a different value now, as long as we wait at least 1 second. So there it is. And we're getting, between -1 and 1 in both directions. Alright, so what we've done here is we've generated a random dart point inside that square, which goes from 1, 1 to -1, -1. So we're going to want to repeat this. Say 10 times. Let's print that. So we'll repeat it 10 times. We'll print the value 10 times. So we're going to need. What we're going to do is throw the dart repeatedly and in a random fashion, and count the number of times it falls within the circle, and compare that and divide that by the total number of times we throw the dart. So actually we can output that'll be the important value. So it'll be something, well, we'll do that later. Let's go ahead and run this, build it, run. So this is our random dart points. The first dart hits this coordinate, the second dart hits that coordinate, and so on. Now what we want to do is count how many times the dart falls within the circle. And we'll have a variable to count that. Call it int. This is number of times it falls within the circle. So we'll say number inside circle, start at 0, and we have the total number of throws. We'll just say number. This should be number. This is number of throws. Say we'll set it to 10. This is number of throws. And then number inside the circle. Let's print that out. Number inside the circle. Second to build. Let's try it. Looks good. So now we have to count. We have to decide whether the dart is in the circle or not. So something like this. If dart in circle, then we will count. We'll increment the number inside the circle. Number inside the circle. And we'll just put, we'll use that increment operator. Every time the dart ends up, the randomly thrown dart is in the circle, we increment that counter. So how do we know if the dart is in the circle? Well, it'll look like this. So we have, we use the distance formula, and it's the distance between the origin and dart x dart y. So that will be, we'll take the square root of that. Actually, we can do it like this, and I'll leave this to you to figure this out. It's dart x times dart x plus dart y times dart y. If it's less than 1, we're in the circle. Eight times we're in the circle. 8 times we're in the circle. Keep ending up there. 7 times in the circle. 6 times in the circle. 9 times in the circle. 9, like that. See? Most of the time we're in the circle. So our estimate now, the ratio, the important point is that the number inside the circle, if we take this ratio, divide by the number of throws, that's the percentage of times we're in the circle. So somehow this is related to pi. Let's see. So if the radius is 1, as in our case, then the area is pi 1 squared, which is pi. So the area is pi. Area of the circle is pi. And the area of the square is 2 times 2, which is 4. So the number of times the dart should fall into the circle is pi divided by 4. So the percentage of times the dart falls in the circle is pi divided by 4. So our estimate for pi can be taken as 4 times this this ratio. So we'll do it like this. Pi equals 4 times this ratio. Let's try it. Pi is 3. This, once again, this is a integer division, so we'll need to make that floating point division. So I'll cast number inside circle to 4. Let's build, run. That's better. Pi is 3.2. Pi is 3.6. Here's our estimate of pi. Now let's improve the estimate by increasing the number of throws. Let's throw the dart 100 times. .28, 3.12, 2. These are way off here, right? 2.76, 3.04. So we're going to need to throw the dart quite a bit. Let's, instead of 100, let's make it 10,000. Let's try to throw this 10,000 times. .128, 3.1488. So it's getting better, but it's still not very good. But this takes time to print this out, so I think it's going to run faster if I take that out, and let's add another 0 to get more accuracy. .14212, 3.13288. So we're getting 3.1. It's pretty consistent, pretty close to the real pi. Let's add another 0. So right now we throw the dart 100,000 times. Let's throw it 1 million. We're going to throw the dart 1,000,000 times. 3.14339, 14189. This one is so it's still varying quite a bit. Let's add another 0. So that's 10 million. What's the largest possible integer? We better check that. What is the largest possible integer for what's the largest possible 4-byte integer? It's a number I should remember. What's the largest possible signed 4-byte integer? So it's 2 to the 32. That's for an unsigned value. So that would be half of that. Looks like it's 4 billion. Half of that is 2 billion. So that's pretty big. So I think we're all set there. We can go to 10 million. 10 million throws. Let's see what happens. I'll have to wait a little bit on that one. Not very long though. Wow, 10 million throws runs pretty quickly. We're getting 3.14 consistently, but the third decimal point, the third digit following the decimal point is varying a little bit, and it's still running quite fast. That's 10 million throws. Let's see. Let's run it 100 million times. It should take a little longer to run. I should pause the video. There it is, 3.14172. Let's run it again. Looks like it takes close to about a minute, half a minute. It's not too bad. Once again, it's 100 million runs. So we're getting some consistency. 3.141 is there. So anyway, that's the end of this exercise.